Welcome to Physics 1305. This is a lecture on Chapter 1. So let's get right to the PowerPoint. Share screen. And here we go. This is just kind of a general overview called About Science. And I'm going to dismiss my image. There's no reason really for you to see it. This lecture will help you understand what science is, scientific measurements, mathematics, the language of science, scientific methods, the scientific attitude, science, art, and religion, science and technology, and physics, the basic science. So what science is a body of knowledge. It's an ongoing human activity. It has beginnings that precede recorded history. In fact, we'll be studying some of the early scientists. It's a quest to understand the laws of nature. Measurements are a hallmark of good science. I'm going to show you some of my measurements that I took. The latest one today in measuring the shadow of a mailbox on the ground. You'll see what I mean when we get to it. And Lord, this is a quote from Lord Kelvin. Often say that when you can measure something and express it in numbers, you know something about it. When you cannot measure it, when you cannot express it in numbers, your knowledge is of a meager and unsatisfactory kind. It may be the beginning of knowledge, but you have scarcely in your thoughts advanced to the stage of science, whatever it may be. Measurements. Measurements relate to how much you know about something. Measurements of pinhole images of the sun nicely lead to a calculation of the sun's diameter. We know that there's it's about 150 million kilometers to the sun, and if you know this distance in this little graphic, there's a ratio of 1 to 110, and from that you can take all sorts of measurements. You can measure the diameter of the sun given that ratio. Okay, this pinhole image would make a round circle that's shown here. These round images of the sun are crescent shaped during a solar eclipse. You can see here the images show up at round. Here they show up as crescent shape. We're going to have two opportunities to see a solar eclipse here in San Antonio. I should have gotten the dates for those, but we'll be blessed by seeing two of them. One will be annular and one will be total. Some early scientific measures. Eratosthenes, the diameter. He measured the diameter of the Earth. He noticed at noon that there was a well that at a particular time of the year that the sun would go straight down to the bottom of the well with no shadow, so it was perfectly vertical relative to the well. At the same time, there was an obelisk that cast a shadow, and the distance was, it formed an arc of 7.1 degrees, and from that he was able to measure the diameter of the Earth. And I did my own experiments. When here it talks about at noon, when the sun was directly overhead, it cast a shadow in this well. Well, when is the sun directly overhead here in San Antonio? At noon? Well, not exactly. For one thing, right now we're at daylight savings time, so everything's ahead by an hour. So let's take into consider, so if it were truly at noon, it would be at 1 o'clock, but it's not at one o'clock. I just took this image on 8/28 2023, and at 13:37 you can see, well, how do I know that the sun is directly overhead? Well, you can see that the sun goes right through the gaps of these mailboxes, and there's so it's just like the well. It's not casting a shadow. As a matter of fact, if I look uh, if I remember looking at the mailboxes at this time, you could even see the rivets casting a shadow on the side of this one. So it was pretty much directly overhead, and it was at 13:37, 1:37, that central daylight time. So if we were on standard time, it would have been at 12:37. Well, it's not exactly noon. Well, you have to remember we're in the middle of the time zone. So maybe it's noon near over by Houston, wherever the time zone starts. And Texas is so big that even El Paso's in mountain time, so it may be more like it may occur more like 2 o'clock in near El Paso before you get when you're still in the central time zone. But so this was when noon occurs, and you'll see that there was there's a meter stick in front of the mailboxes, and I use that meter stick. If you observe the sun, you'll see that it was almost directly overhead during the peak of the summer, or during the summer uh, equinox, and ever since then, the shadow of this mailbox has been lengthening. Here's 3 examples. I just put a meter stick in front of the box, and on August 14th, it was at like 57.5 centimeters. On August 24th, it was 66.3. I'm going to call it. It's a little fuzzy where the shadow actually is casting, and on 8/28, which happened to be today, it was right at 70 centimeters. So you can see how the shadow has been lengthening over time. Well, these photos don't show you anything. So you want to turn your observations into data. And here I plotted, you can see I've done more than just 3 dates. I can't always get it either. We're busy and I'm not able to be at my mailbox at 1:38, 1:37. It has been 1:38, and it seems to be progressing more to 1:37. It'll probably be 1:36 or 1:35, or even less by the time we end daylight savings time. And so it'll be 12, let's say 12:35 when we go to Central Time. Anyway, here's the data, and you can see that the first data I took, it's about at 47 degrees, and today it was at 70 degrees. So you can see that the shadow has been lengthening over time. So here's data. This is what scientists do. They take measurements and they present it as data. So here's some of my own data that I've taken just from being interested in seeing how the rate at which the shadow progresses from our mailbox. Okay, Aristarchus measured the distance and size of the moon using knowing that using the solar eclipse and the lunar eclipse, and the Earth's shadow was 2.5 times wider than the moon during a lunar eclipse, and we won't go much into that, but Aristarchus used very ingenious methods to measure these. The light rays from the sun are not exactly parallel because of its size. It's so large compared to the Earth and the moon both. Okay, mathematics. Mathematics is the language of science. Now, we're not going to get into any calculus. I don't even think we're going to do much algebra, but we will have to do some math just to get, learn about speed and velocity and acceleration. We will need some mathematics. It's not going to be very deep, but you are going to use some math to do science, to do the physics that you study, the integration of science and mathematics. Mathematics is the natural language of science. Ideas of science are unambiguous when expressed in mathematical terms. Equations of science provide expressions of relationships between concepts. Equations are guides to thinking. This is just like my graph here is if it's not exactly straight, it's probably because it's a little hard to get the edge of the shadow as I'm taking measurements. But here I've taken data and I use the graph to interpret, and you can see how the shadow lengthens. It'll be interesting at the winter solstice to see this is going to reverse. So it'll probably end up looking in somewhat the form of a sine wave. You can see it if you have a globe at home. Look at the globe, and most likely on the side of the globe, it's usually in one of the oceans, it shows you an analemma, and it shows you the angle that the Earth is to this relative to the sun for any date, and you can see how the angle changes over time. We're going to see, if you will, an analemma laid out. If I could keep this up over the year. Okay, let's get back to where we were. Scientific methods. There is no one scientific method. In general, scientific methods refer to principles and procedures for the systematic pursuit of knowledge, involving the recognition and formulation of a problem, the collection of data through observation and experiment, and the formulation and testing of hypotheses. And it can be over a number of things. One of my hobbies is baking sourdough bread. Every few days, I make another batch of sourdough. When I first learned about it, I had I looked up YouTube videos, and my daughter gave me a sourdough starter, and they gave me some recipes. You use the sourdough starter, some salt, some water, and just flour, all-purpose flour. I made it, and it was very, very wet, hard to handle. It stuck to your fingers. So I slowly reduced the amount of water I used. I started off, I think, with 70% hydration, and I'm down now to about 55% hydration, to something that I find more manageable. But it took experimentation. It took reducing the water content of my recipe until I came up with a batch that was easy to work with. And so basically I used experimentation. I didn't just, I changed the ratios of water to flour systematically, not just randomly, and that helped me find a good point of hydration for my sourdough bread. Okay, scientific methods, common steps. Like it said in the last scripture, there is no one, but these are some basic principles. Number one, you recognize a question, a puzzle, an unexplained fact. My question was, why is this thing so wet? What can I do to make it not so wet? You make a hypothesis. An educated guess to resolve the puzzle. Reduce the amount of water in my sourdough recipe. Predict consequences of the hypothesis, and then perform experiments or make calculations to test the predictions. Well, my calculations were just using ratios to see how much water to go with 500 grams of flour, and I eventually came up with 275 grams to come up with a nice sourdough loaf. And then you formulate the simplest general rule that organizes the three main steps. So now I've come up with a satisfactory recipe for my sourdough bread, and I make it often. Okay, the scientific attitude. The scientific attitude is one of inquiry, experimentation, and a willingness to admit error. Into that inquiry, I'm going to add observation. You need to observe. You need to be observant of different things, like being observant to notice that the shadow of the mailbox was changing day to day. So I got a meter stick and started measuring it. So observation is part of it. Inquiry, well, which way is the shadow going to lengthen? And then experimentation, going out there, not every day. It's some days are cloudy, some days I'm away, but the experimentation is taking measurements, and then willingness to admit an error. Well, if I find that I'm doing something wrong, be willing to admit it and correct it. Okay. Scientists are experts at changing their minds. You must accept experimental findings. You test for erroneous beliefs, and you understand objections and positions of antagonists. You can't stick with an idea and say, come up with data that contradicts your idea and say, oh, well, this is the reason why it didn't work. My idea is still correct. No, you have to change your idea. You have to change your mind about, okay, my initial idea was wrong. And you go about fixing it and accepting the truth of the data that you've taken. Okay, the scientific attitude. Fact is a close agreement by competent observers who make a series of observations about the same phenomena. Again, observation is the key point to science. Facts are revisable data about the world. Theories interpret facts. A scientific hypothesis is an educated guess that is only presumed to be factual until supported by experiment. So it's the experimentation that helps you verify your hypotheses. You can come up with a hypothesis, but if it can't be proved with an experiment, then it's probably of no use, no practical use. Okay, which of these is a scientific hypothesis? The moon is made of green cheese. A. B says the atomic nuclei are the smallest particles in nature. C, a magnet will pick up a copper penny. And D, cosmic rays cannot penetrate the thickness of your conceptual physics textbook. So as ridiculous as A is, the moon is made of green cheese, all of these are really scientific hypotheses. The explanation here, all are scientific hypotheses, all have tests for proving wrongness. So they pass the test of being a scientific hypothesis. Okay. Which of these is not a scientific hypothesis? Protons carry electric charge. Undetectable particles are some of nature's secrets. Magnetic fields deflect moving charged particles. All of the above are scientific hypotheses. Well, the answer is not all of them are scientific hypotheses. If you have a particle that's undetectable, then you can't prove it wrong. So B is not a hypothesis. Undetectable particles are some of nature's secrets. Well, if you can't, if it's hidden, if it's undetectable, then you can't test it. You can't disprove it. So choices A and B can be disproved by experiments. Choice B has no test for wrongness, so it is not a scientific hypothesis. Okay, the scientific attitude, the difference between a law and a theory. Law or principle is a hypothesis that has been tested repeatedly and has not been contradicted. The theory a synthesis of a large body of information that encompasses well-tested and verified hypotheses about certain aspects of the natural world. And we'll learn about Newton's laws of gravity. They held for, and they do hold for uh, large systems. But when you start getting down into the atoms and the subparticles of atoms, they don't hold. So there had to be new principles that came into play when we went to the small scale. Which of these may change over time with further study? Facts, theories, both of the above, or neither of the above? Well, the truth is both of them can change. As we learn new information, we refine our ideas. Likewise, in science. Okay, a person who says that's only a theory doesn't likely know that a scientific theory is a guess, a number of facts, a hypothesis of sorts, or vast synthesis of well-tested hypotheses and facts. Well, the answer is D. The word theory in everyday speech is different than its use in science. In science, only a vast experimentally verifiable body of knowledge is a theory. Okay, science, art, and religion. Comparison of science, art, and religion by domain. Science is of the natural order and involves the discovery and recording of natural phenomena. Art is the interpretation and expression of human experience. Religion involves faith and worship of a supreme being. So the similarities between art and science: knowledge of what is possible in human experience and nature. Knowledge of both affects our views and decisions about the world. And similarities between religion and in science both deal with unanswered questions. Between a pilot and a priest, who do you think should fly a commercial jet airplane? And who do you think should perform a marriage? Although these questions are no-brainers, they have a point. The pilot should fly and the priest should perform a marriage. The priest should fly and the pilot should perform a marriage. The pilot should do both and the priest should do both. Well, the correct answer in this case is A. The pilot should fly and the priest should perform a marriage. I mean, the pilot and priest have different skills for different tasks, and each can do their thing well. It's possible that, I guess, that a pilot could be a clergyman, and it's possible that a priest has a pilot's license, but that's not typically the case. Before we go on to that, it doesn't mean that there's a dichotomy. I mean, a scientist can't be religious, and a religious person can't be a scientist. Some of the early scientists, Copernicus, Galileo, even Newton. And Newton wrote more about religion than he did about physics. So some of the early scientists were strong believers. Well, some people say, "Oh, well, that was just the culture of the time." Well, I think their faith led them to make some of the discoveries that they did. Okay, let's move on. Science and technology. Science is concerned with gathering and organizing knowledge. Technology is the use of scientific knowledge for practical purposes and to provide tools for further exploration. To me, technology is applied science. Pure science is just finding out about stuff. Technology is applying that new stuff that we've learned in our pursuit of science. Okay, let's see. Physics, the basic science. Physical sciences include geology, astronomy, chemistry, and physics. Life sciences include biology, zoology, and botany. And physics underlies all the sciences. I have a hard time with chemistry. To me, there's a lot of memorization. In physics, a lot of it, I mean, once you get an understanding of it, you derive a lot of the formulas that you need. Um, so physics underlies all the sciences. Okay, when compared with the fields of chemistry, biology, geology, and astronomy, physics is the hardest, the central science between chemistry and biology. Simple enough, but only for especially intelligent people. That the last one is not true. It is the most fundamental of the sciences. Although physics may be the most difficult science course in certain schools, when compared with the fields of chemistry, biology, geology, and astronomy, it is the most fundamental. Physics underlies all of chemistry, which in turn underlies biology. Geology and astronomy are also controlled by the laws of physics. Thus, physics is the most basic of the sciences. Okay, and that brings us to the end of this chapter. I'll have more. Uh, I'll produce chapter 2 later this week. Don't know that I'll assign much homework, and if I make a quiz, it'll be very, very simple. It'll be easy to pass. So uh, that's it for this this lecture.